Hello everyone, thank you so much for coming out today. We are Project 4 and we're here to present our prototype, Pepper. My name is Jalissa and this is our team. We are all Vanderplow Luminsoity scholars and we come from a background of majors. Now I'm going to pass it to Paige to talk about the current problems that we're trying to solve.
Thank you, Jalissa.
Thank you, Jalissa. So let's take a look at our current problems. So currently, astronauts have to eat extremely processed and unappetizing food, whether it be freeze-dried or vacuum-sealed. It's just overall not a great experience. And the food also lacks nutrients such as vitamin D, calcium, and folate. This leads to problems such as, above all, malnutrition, and also weight loss, muscle atrophy, bone density depletion, and fluid loss. Let's look at some statistics. So data from NASA studies show that 2% of bone mass is lost per month that an astronaut is in space. They also consume 25 to 30% less food than they did before their missions. It is also shown that 10 to 15% of their body mass is lost by ISS crew members. And this is extremely harmful, as if they were to lose 30%, it would be considered lethal. I'm gonna hand it to Nabia to look at some current solutions.
Paige? So, as mentioned previously, astronauts are currently eating highly processed foods in airtight packaging that's often velcroed or taped to a tray, resembling a school lunch, except more processed and less appealing. If you thought school lunch was bad, try astronaut food. They eat the same foods every single day with little to no seasonings and still aren't getting enough nutrients that they need to last throughout their entire missions. So, the current solution is to have them take pills alongside their meals. So they're eating pills and bland food every single day. Delicious. So I'll pass it off to Jordan to talk more about how our project solves this issue.
Yes, so you may be wondering what PEPPER really stands for. PEPPER stands for Project Engineered Plant Production for Extraterrestrial Research. Our goal is to provide astronauts with dependable and 24/7 access to foods fresh and rich in nutrients. I'll now pass it off to Diana to talk about hydroponics.
Now you may be, thank you, Jordan. Now you may be asking yourselves, why hydroponics? Well, hydroponics is a system that uses no soil, but instead water-based mineral solutions. Some of the benefits are that it is water saving, and it is water saving because it is in an enclosed system, and since it's in an enclosed system, it creates a cycle that allows the water to be reused. There is also fast growth because you can manipulate the nutrients that the plants are getting, so you can manipulate if they grow faster or slower, or depending on that, like that's the growth. There is no soil because it is hard to replicate soil's nutrient cycle in space. And without the soil, there would be no weeds, and without the pests, there would be no pesticides. I will now be passing it to Sydney to talk about the competitor analysis.
Thank you, Diana. So I'm going to go ahead and give a little overview about how Pepper compares to two different competitors that are on the ISS right now. The two major competitors that we have are Veggie and PWM, or their Plant Water Management Experiment. The Plant Water Management Experiment is on here because it is an experiment on the ISS that deals with capillary flow, and it is experimenting with hydroponics. So this is why we chose to compare it with Pepper. As you can see, on the far left at the top, Pepper is a hydroponic system, which does compare to the Plant Water Management Experiment. Next, Pepper is a modular system, which means that it is kind of like a building block aspect, so we can combine different systems together to grow multiple plants at the same time. With Pepper, we can also control the nutrients that the plant is receiving, just as Diana talked about, and with that, it can fit large plants, which is also a positive because it's also compact design at the same time. We can also control all of the environmental aspects for growing the plant, which is a notable aspect of Pepper because it does have the same thing with Veggie and the Plant Water Management Experiment. Now I'm going to pass it off to Ethan to talk about the inner workings of Pepper.
Thank you. So our model can be split up into three main parts. At the very top, we have the grow chamber. At the bottom, or at the middle, we have the root chamber. And at the very bottom, we have the water tank. And then on the sides, you can see the various pumps and piping that connect the root chamber down to the water tank and vice versa from the water tank back up to the root chamber. So first, we have the grow chamber. Its main purpose is to hold the top part of the plant and provide space for it to grow. It also has lights at the very top that turn on and off periodically every 12 hours or so. Then we have the root chamber. This is a mostly watertight tank that has the roots growing in from the very top. It also has 3 pipes coming into it that are connected to 3 different nozzles. At the very bottom, we have a low pressure water nozzle. This one shoots in water at a low pace so it can circulate the water that's already in there so it doesn't remain stagnant. Then in the middle, we have an air nozzle. This one pushes air into the tank so it can clump up onto the roots and oxygenate the plant. Now these 2 nozzles will be running simultaneously, and after they run for a good amount of time, they will turn off and the top nozzle will turn on. Now this one's a high pressure water nozzle, so this one shoots in water at a higher speed so it can knock off any air that is accumulated on the roots. All this additional air and water that has been shot into the tank will be able to leave via the outtake pipe, which is connected down to the water tank. Now the water tank is mostly water on the bottom side and has some air on the top side. And when the air and water come in from the outtake pipe and into the water tank, what happens is they separate due to capillary forces, which pushes up the air to the top side where it can rejoin with the rest of the air. And lastly, on the side, we have 3 more pipes, 1 at the very top that collects the air and 2 on the bottom for the low and high pressure water valves. So that brings it back up to the root chamber. So now I'll pass it to Luca to talk more about our 3D CAD model design.
So this is the CAD model that we based our prototype off of. As you can see, they're pretty similar. For the prototype, we chose to make it out of T-slot as well as laser cut acrylic and wood, and finally some 3D printed materials. Similar to what Ethan just talked about, the interior looks like this. We have the grow chamber on top, and directly below that is the root chamber. And directly below that is the water tank, and surrounding these pieces is the electrical and the pumps, which Navia is going to go over in further detail.
Oh. So the major components have already been covered, but I'll just go over the electrical section. So this is our schematic, and the 4 major components being the grow lights, the aerator, and then the high pressure and low pressure pump, which is controlled with an Arduino. All of these components are 12 volts. Now that we've covered every aspect of our prototype, I'll pass it off to Jalissa, who will talk about where we plan to take this project in the future.
Thank you, Navia. So we're going to be getting some feedback and refining our prototype, and we're hoping that with these changes, our prototype will be ready to enter into a NASA competition a few times a year, and NASA holds these competitions, and we're hoping that we could enter our prototype in one of these or an MIT Solve Global Challenge as well. And we're hoping that through one of these avenues, we could get our product implemented onto the ISS so that we can ensure healthy bodies and healthy missions. Thank you so much for coming out today. Are there any questions? Yeah, so one of the reasons that our system is efficient for space is that sending produce up to the ISS already grown is super expensive and really difficult and impossible to do with any frequency. But seeds are much lighter and easier to send up, so we're hoping that the system could give astronauts a more continuous supply of this produce. And as well, since our system is hydroponic, there's no soil that has to be sent up there, which saves a lot on weight because the water is a closed system and can be continuously recycled through. And as for regarding how many vegetables we can hope to grow with this, it really depends on how much space on the ISS we would be given for this system. Our system is modular, so depending on how much space they give us, we could keep adding plants and see how much we could produce.
So I have a question. What's your power consumption rate for the system?
So, as mentioned previously, it's just 12 volts for the entire system. But but for the one that we'd send to the ISS, it would probably be just a little bit more.
Thank you.
Great presentation. So my question to you guys is, what about this project surprised you the most? Like whether it's in your research or your actual prototyping, what was the most surprising aspect?
So what personally surprised me the most, I would say, was just seeing our prototype come together. Personally, I'd never built anything like this before, so seeing our ideas from a paper go into a physical model that actually worked, like, surprised me to see just how it came together and what that whole process was like.
I just want to add on to what Jalissa said. What was especially surprising for me is like, you obviously understand how a hydroponic system works, but it gets really complicated once you put it into space, because then the aeration doesn't just flow straight up, it'll just like float around, and that's why we have the high pressure and low pressure pumps implemented.
What was the most challenging part of this whole thing for you?
So kind of similar to what Navia said, it was really hard to work with the microgravity. It's something we take for granted on Earth, like we live with it every day, and to adjust to that was a little difficult in our design. And we kept coming up with these solutions and then thinking about it and going, oh wait, that doesn't work anymore. Then we'd come up with something else and be like, oh, that doesn't work either. And so the iterations had to keep coming until we finally landed on a design that would work in microgravity.
So do you have any design points or decisions that for version 2 you already know you want to make that adjustment now?
Yeah, so this model currently only operates with the high and low pressure nozzles. We don't have the actual aeration system because it doesn't work on Earth. But we'd like to test that, so make a model and kind of simulate that as best we can on Earth.